In the sixth lecture, we will cover the central limit theorem and the confidence interval. The central limit theorem states that the sampling distribution of the sample mean will be nearly normal if the sample size is large enough. The theorem is valid even if the population distribution is not normal. If the population distribution is normal, then the sampling distribution is normal even when the sample size is small. The central limit theorem also explains why the sampling distribution is very important and why the normal distribution is the most important distribution in statistics. The central limit theorem helps us avoid the joint distribution of the sample and make inference in a more direct way. It is practically important to know how large the sample size should be. We may use n larger than or equal to 30 as the standard requirement. However, if the population distribution is distinctly not normal, then it may even require a larger sample size. To strengthen the concept, here is a multiple choice question. What are the requirements for the sampling distribution to be nearly normal? A. The population distribution is nearly normal. B. The sample distribution is nearly normal. C. The sample size is large enough. D. The sample is a random sample. The answer is C and D. The sampling distribution will be nearly normal if we have a random sample and the sample size is large enough. Choice B is not correct since the sample distribution is different from the sampling distribution. Choice A is not correct since the sampling distribution could be nearly normal even when the population distribution is not normal. Now we learned how to get a random sample using probability sampling methods, and the central limit theorem tells us that the sampling distribution will be nearly normal when we have a large sample size. For example, we would like to make inference on the average height of male adults in the US. Let's say we already have a random sample of 10,000, and the sample mean is 70 inches. We know the mean of the sampling distribution of the sample mean is unbiased for the population mean. Thus, the sample mean is a point estimate of mu. But the point estimate is not enough. We need the interval estimate that may tell us how accurate the estimate is. Confidence interval is an interval estimate. It consists of two parts, a point estimate and a margin of error, which is estimate plus minus margin of error. The margin of error is the product of the multiplier and the standard error. It indicates how far an estimate may be from the parameter. In order to get the margin of error, we need to set the confidence level, also called confidence coefficient. It tells how confident we are about the confidence interval. Although we may hear something like, I'm 100% sure in daily life, in statistics, this does not happen. We cannot be 100% confident when we make inference. Also, we should not confuse the confidence level with the significance level, which we will introduce later. The significance level is used in hypothesis testing, and the confidence level is used in interval estimation. Normally, the confidence level is the complement of the significance level. For example, the standard confidence level is 95% and the significance level is 5%. Now, how to interpret we are 95% confident? The sampling distribution is based on all possible random samples. We may calculate the 95% interval for each sample. Among all random samples, 95% of the resulting intervals contain the parameter. In the last slide, we learned that the margin of error is the product of the multiplier and the standard error. We know that the standard error is the population standard deviation divided by square root of n. Thus, if the population variance is known, then we may calculate the standard error. In this case, the multiplier is a z-score that corresponds to the required confidence level since the sampling distribution of the sample mean is normal. The table below shows the z-scores corresponding to some common confidence levels. For example, the 95% confidence level has a z-score of 1.96, which is approximately 97.5 percentile point of the standard normal distribution for a two-sided interval. Also, we may use this Excel function. Since the confidence interval is normally two-sided, we may transform confidence level to P using this formula. For if we would like to calculate one-sided confidence interval, then P is equal to 1 minus confidence level for the left-sided confidence interval and P equal to confidence level for the right-sided confidence interval. Also, z-table can be used to calculate the z-score, as we may learn from a statistics class. From this, we may have the margin of error. The margin of error increases with the confidence level because if we would like to be more confident, then we need to have a wider interval to include the parameter. The margin of error also decreases with the sample size because the estimate is more accurate when we have a large sample. Actually, the margin of error is inversely proportional to the square root of n. Here is the height example. We know the standard deviation of the adult male height in the US is 3 inches. Now we have a random sample of 10,000 and the sample mean is 70 inches. What is the average male adult height in the US? For this problem, we know sigma is 3, n is 10,000, and y bar is 70. The sample is random and its size is large enough for its sampling distribution to be nearly normal. The standard error is sigma divided by square root of n, which is 0.03 inch. For 95% confidence level, the multiplier is 1.96. Thus, we have the margin of error is 0.06 inches. Due to the large sample size, the margin of error is pretty small compared to the estimate 70 inches. Thus, the estimate is quite reliable. The 95% confidence interval is 70 plus minus 0.06 inches. We are 95% confident that the average male height in the US is between 69.94 and 70.06 inches. We should be careful how to interpret the confidence interval. First, the inference is about the parameter and not about one sample or one observation. Second, the chance is associated with all random samples in the sampling distribution. These 2 points will help us answer the multiple choice question below. Which of the following statements are right about the 95% confidence interval calculated in the previous example? A. If we repeatedly take samples, 95% of the average male adult height of the samples may fall in the confidence interval. The average male adult height of the samples is the sample mean. We are only interested in the parameter, and the statistic is used to estimate the parameter. Thus, A is not correct. B. If we repeatedly take samples, 95% of the confidence intervals from the samples may contain the average male adult height in the US. The parameter is the average male adult height in the US, and the connection is between confidence interval and the parameter. The chance is associated with all samples, thus B is correct. There is 95% chance the average male adult height in the US is in the confidence interval from the sample. The average male adult height in the US is the parameter. Both the parameter and the confidence interval from the sample are fixed. There is no probability here. The chance should be associated with all samples. Thus, C is not correct. D. We are 95% confident the average male adult height in the US is in the confidence interval from the sample. This is how we interpret the confidence interval. 95% confidence level tells us a chance for all possible samples, not only one sample. D is correct. We should notice the difference between the chance and the confidence. E. There is 95% chance that any male adult height in the US is in the confidence interval from the sample. This inference is not about an individual observation. Inference about an individual observation is related to a prediction interval. Prediction intervals tell us where we can expect to see the next observation. Prediction intervals must account for the uncertainty in estimating both the parameter and the individual observation. So, a prediction interval is always wider than a confidence interval. Thus, the E is not correct. In summary, we learned the central limit theorem and the confidence interval in this lecture. The central limit theorem states that the sampling distribution of the sample mean will be nearly normal if the sample size is large enough. The theorem is valid even if the population is not normally distributed. In practice, we may use n larger than or equal to 30 as the standard requirement. The central limit theorem helps us avoid the joint distribution of the sample and make inference in a more direct way. Confidence interval is an interval estimate. It consists of two parts, a point estimate and a margin of error. The confidence level, also called confidence coefficient, tells how confident we are about the confidence interval. 95% confidence means among all random samples taken in the sampling distribution, 95% of the resulting intervals contain the parameter. The margin of error is the product of the multiplier and the standard error. It increases with the confidence level and is inversely proportional to the square root of the sample size, n. The interpretation of the confidence interval for a 95% confidence level is we are 95% confident that the parameter is in the confidence interval calculated from the sample. The inference is about the parameter, not about samples or observations. The chance 95% is based on all possible samples in the sampling distribution.